So in today's video, we're going to look at chapter 7.2, which looks at quadratic forms. Quadratic forms are just a type of function that act on Rn. So they act on n space. And we tend to define a quadratic function, we call it Q, and it's going to be defined on Rn. So x is going to be this vector in Rn. And it's defined by x transpose Ax, where A is just going to be an n by n symmetric matrix. Okay, now, if A is a symmetric matrix, it's n by n. When you multiply it by x, you're going to get an n-dimensional column vector. So I've got an n-dimensional column vector, and then x transpose is going to be an n-dimensional row vector. So what I have here, Qx is essentially just this n-dimensional row vector times this n-dimensional column vector, which will end up at just a real number. So this function is going to take Rn back to just the real space, okay? The simplest type of quadratic form is when you have A is the identity matrix. When A is the identity matrix, you end up with Q of x is equal to x transpose I x. Now the identity times any vector is just the vector itself, so I'm going to end up with x transpose x. That is the same thing as taking x dotted with itself, okay? If you think about when we do the dot product, this can also be seen as just the magnitude of x squared, because remember, when we take the magnitude, we're going to be multiplying each of these vectors, each element in x by itself, and then we're going to square root, okay? So in this case, I'm just not square rooting, so if I take the dot product of x with x, I'm going to get the magnitude of x squared. Whatever your matrix A is always called the matrix of the quadratic form. Okay, so whatever your matrix A is, it's got to be a symmetric matrix. It can be a diagonal matrix because any diagonal matrix is symmetric. But for whatever symmetric matrix you have, that is the matrix of that particular quadratic form. So for each quadratic form, A is going to change. You plug in a vector x and you're going to get values out depending on the value of x. An example of this, we'll do a quick example. If I take A is equal to this 2 by 2 matrix, okay, and I want to find Q of x just for this general two-dimensional vector x, okay, so I want to just find what Q of x is. I'm not looking at a particular value at a particular x vector. I'm just looking for a general form, okay. If I do this, I know that Q of x is going to be x transpose Ax. X transpose is the row vector x1, x2. A is going to be 3, negative 1, negative 1, 4. And then I've got x1, x2. Okay. If I multiply all of this out, okay, we'll start with this part of the equation. I'm going to get x1, x2. And then my first row, remember I do row times column. So the first row of this vector is going to be 3x1 minus x2. And my second row is going to be negative x1 plus 4x2. Okay. Then I've got a row vector times a column vector. Remember when you do matrix and vector multiplication like this, I can do row times column. The dimensions match here because I have a 1 by 2 vector times a 2 by 1 vector. I'm going to end up with a 1 by 1. That's a scalar, okay? So when I multiply this out, I'm going to get x1 times this first row here plus x2 times this second row. When you do that, I'm going to simplify it down, but what you should end up with when you do that and simplify it down is this equation. Okay. So I basically have a quadratic here in terms of x1 and x2. Okay, that's why it's called a quadratic form. However, you'll see here, if x if A would have been a diagonal matrix, okay? So if A would have been diagonal, meaning that both of these terms here, these negative ones, would have instead been 0. That would have made this matrix diagonal. If both of those elements were 0, okay, let's come down here and see what would have happened if both of these were 0. Well, I wouldn't have had this negative x2 term here, and I wouldn't have had this negative x1 term here. Both of those wouldn't be there. So then when I multiplied this row vector times this column vector, I would have just ended up with the 3x1 squared plus 4x2 squared, okay? I wouldn't have had this like mixed term here with x1s and x2s, or if you've got more elements in x3s, okay? I wouldn't have any term that was made up of different xi's, okay? I would have just had these squared terms. We tend to call these terms the cross product terms. So any term that is mixed with xi's, so you've got different xi's within the same term, you tend to call it the cross product term. Okay. So if A would have been a diagonal matrix, I wouldn't have had that cross product term. Okay, so if A is diagonal, there's no cross product term. Okay, so keep that in mind, because remember, we like things to be diagonal. It makes our calculations so much simpler. Okay, and we'll see why in a second. Okay. What I want to do is go backwards on a similar example to what I've just done here. So here I was given this matrix of the quadratic form, and I found the equation of the quadratic form. I want to go backwards here. I want to see if, given this equation of the quadratic form, can I go back and find the matrix? So let's do this example. This one's going to be a 3 by 3, but no matter how large this equation is, how many xi's we've got in there, you'll actually see it's very simple to figure out what the matrix is. So let's say that q of x was equal to 3x1 squared plus 2x2 squared minus 5x3 squared minus 6x1 x2 plus 8x1 x3 minus 4x2 x3. Okay, and I want to find the matrix A such that q of x is equal to x transpose AX. I want to find that A matrix. Let's go back to our previous example. Okay, what you will notice when you look at this equation here is that each coefficient in front of an xi squared term was just my diagonal entry. So my first diagonal entry was the coefficient of x1 squared. My second diagonal entry was the coefficient of x2 squared. And if you carry on like this, the coefficient of x3 squared would have been the third diagonal element had you had a larger matrix. So I already know that my entries on the diagonal are 3, 2, negative 5. So I've got that part already. So I know I'm dealing with a 3 by 3 matrix for a start, because I've got up to x3. So I've got 3, 2, and negative 5. Now I need to look at the off diagonal elements. So let's go back to here. When we did this, okay, and you multiplied it out, I've got negative 2 times x1, x2. So you'll see from the way that we got this cross product term, this negative 2 x1, x2, was by taking negative x1, x2, which came from this term here with this term here, minus x1, x2, which came from those two terms multiplied together. So the way that those two came about was because of these two entries here, which was because of these two entries here. So this negative 2 came about because I had a negative one here plus a negative one here. So all I have done for each of these cross product terms, I have that this negative 2 is split in half between the 1, 2 entry, this entry here in the matrix, and the 2, 1 entry, this entry here in the matrix. So for each xi, xj cross product term, okay, the coefficient of xi, xj is split in half between the ij entry and the ji entry. So let's come back to here. I've got negative 6, x1, x2. So I need to split negative 6 in half to two negative 3's. I'm going to have negative 3 in the 1, 2 entry and a negative 3 in the 2, 1 entry. So I'm going to have a negative 3 here and a negative 3 here. Carry on in this way. So I've got a positive 8 here. Split that in half. I'm going to get 2 lots of 4. So I want a 4 in the 1, 3 entry and a 4 in the 3, 1 entry. So that's going to give me a 4 here and a 4 here. And finally, I've got a negative 4. Split in half will give me 2 negative 2's. And I'm going to have a negative 2 in the 2, 3 entry and a negative 2 in the 3, 2 entry. So this is my matrix A. Okay, so it's actually really simple to see what happens and how we actually get this matrix just by looking at this quadratic form as an equation. If you want to, whenever you do this, you can always go back and check by just then multiplying x transpose AX for just this random x1, x2, x3. You could go ahead, multiply that out with this matrix A, and you should end up back at that quadratic form. If they ever say to you, what is the value of q of x is equal to this quadratic form for a particular A, and they give you an x value at which to evaluate it at. So let's say that they gave you q of x is equal to x transpose AX, where A is this. Go ahead and find the value of q at the vector x is equal to 1, 2, 3. All you have to do is go ahead and plug in 1, 2, 3. So you could either go ahead and plug x into this and take x transpose times A times x, or if you have the equation form of it, and they want the value of q at this particular vector x, you just plug in x1 is equal to 1, x2 would equal 2, and x3 would equal 3. You just go ahead, plug those values in, and you will get out the scalar for q. Okay. So if they ever ask you what the value of q is at a particular vector x, just go ahead and plug the numbers in. Now, as we've said before, and I mentioned this earlier, if you have no terms in the off-diagonal entries, so let's say you have this matrix A, I'll come back to here actually, you've got this matrix A. If we have no non-zero entries in our off-diagonal entries here, so if all of those were 0, you would have this diagonal matrix. And when you have a diagonal matrix for the matrix of a quadratic form, what that does for your equation of the quadratic form is it gets rid of these cross product elements. So I would, in this case, have no x1, x2 term, no x2, x3 term, and no x1, x3 term. Okay, so whenever you get one of these, if A was a diagonal matrix, which means that all the off-diagonal entries are 0, it means that when you multiply this out and get the equation for the quadratic form, you're going to have no cross-product entries. You're only going to have like x1 squared, x2 squared, etc. We like this because it makes stuff a lot easier. Okay, it makes all of our calculations a lot easier. We just like diagonal matrices. It's like back when we were diagonalizing matrices. It just makes stuff so much easier with calculations when you know that you have this diagonal matrix. What you can actually do, if you have this equation, this quadratic form, x transpose AX, where A is just a symmetric matrix, it's not necessarily diagonal, it's just symmetric. You can actually do something to this quadratic form and do a change of variable to actually have the quadratic form in terms of a diagonal matrix. The way that you do this, okay, normally you've got this quadratic form x transpose AX, where A is just symmetric, okay? X is just a vector in Rn. So what I'm going to do is I'm going to do a change of variable on it by taking this vector X in Rn equal to this n by n invertible matrix P times Y, okay? Y is just this other n-dimensional vector in Rn, okay? I'm actually going to put another restriction on this change of variable matrix P in a second, as you'll see. But I'm just going to let X equal to P times Y, okay? So I'm going to be doing a change of variable for Q of X, and I'm going to make it into Q of Y. If this is the case, we know that Y would equal P inverse X. And as I said, I'm going to put another restriction on P in a second. But if we go ahead and do this, I know that X transpose AX, I can now substitute in X is equal to P of Y, P times Y, which is going to give me this. When you transpose a product, you take the product of the transposes in the opposite order, so in reverse order. So you're going to have Y transpose, P transpose, A, P, Y. Now, because of this thing, if I actually distribute this slightly differently, so I put parentheses about P transpose AP, I now have, I can call this matrix whatever I like, but I have an n-dimensional vector transpose times this n by n matrix, because I've got 3 different n by n matrices multiplied together here. I'm going to get an n by n matrix in the middle, times this n-dimensional column vector. This is exactly the same form as what I have up here, okay? N-dimensional row vector times an n by n matrix times this n-dimensional column vector. So now P transpose AP is the matrix of the quadratic form. Okay. Now, I said to you a second ago that we can choose P kind of strategically so that this thing actually comes out to a diagonal matrix. You'll remember from the previous chapter that if A is symmetric, then we know that we can find this orthogonal matrix P such that A is similar to this diagonal matrix D by using this orthogonal matrix P. So not only does A equal PDP inverse, it actually equals PDP transpose because P is orthogonal. So if when I do this change of variable up here from X to Y, if I require that P is an orthogonal matrix, I know that P transpose equals P inverse. Okay, remember an orthogonal matrix is just an orthonormal matrix, so it's got orthonormal columns, but it is square. Okay, so A is equal to PDP transpose, which means that when I go ahead and solve for D instead, I can pre-multiply both sides by P inverse or P transpose, and then I can multiply on the right on both sides by P. So I actually end up with D is equal to P transpose AP, which is exactly what I have up here. So if I choose my change of variable in such a way that P is an orthogonal matrix and A we know already is symmetric, I know that I can make this P transpose AP to be diagonal. So that means that D is now the matrix of the quadratic form and it is diagonal. So I can always write, as long as, because we know that any symmetric matrix is going to have this orthogonal diagonalization. Okay, so I know that for any symmetric matrix A, I can find this P such that that is the case. Okay, because I know that every symmetric matrix A is going to have this orthogonal diagonalization. So as long as I choose that matrix P to do my change of variable, I can then go ahead and say, well, I can say that we'll call it Q of Y is Y transpose dy. So I can always write my quadratic form in terms of Y and this diagonal matrix D, and therefore this quadratic form where I've done this change of variable from X to Y is now only going to have this y1 squared, y2 squared, y3 squared. It's not going to have any cross product terms. So by doing this change of variable, I get rid of my cross product terms, and it makes my calculations a lot easier. If you go ahead and look at page 405, figure 1 on that page is going to show you the mappings and how this all works and what matrix maps what to what. And you can see how this change of variable works as a picture. So go ahead and look at figure 1 on page 405. So let's go ahead and do one of these change of variable problems. So for an example, let's say that I have this quadratic form Q of X, and that's going to equal 2x1 squared plus 6x1 x2 minus 6x2 squared. And I want to make a change of variable that transforms this into a quadratic form with no cross product terms. Okay, so looking at my quadratic form right now, I want to find my matrix A, my matrix of my quadratic form. Well, I know that my diagonal entries are 2 and -6. And then I'm going to have 6 split in half between the 1, 2 and the 2, 1 entry. So I know that I'm going to have 3 and 3. So this is my matrix of my quadratic form. Now, what I want to do is orthogonally diagonalize this matrix and find that diagonal matrix D with that, in this case, orthonormal matrix that is made up of the orthonormal basis that's made up of the columns of P. And therefore I've orthogonally diagonalized my matrix A, and I can go ahead and find what this change of variable is. So then I can write my quadratic form in terms of just y1 and y2 with no cross product term. Okay. If you go ahead and find the eigenvalues and eigenvectors, that's always the first step whenever you orthogonally diagonalize. Okay. So your two eigenvalues are -7 and 3, and the corresponding eigenvectors are -1, 3 and 3, 1. Okay. Now, we've got a symmetric matrix. It has distinct eigenvalues. We know that the eigenspaces that correspond to distinct eigenvalues are already orthogonal to one another. So we know that the dot product of these two vectors is already 0. We know that they're orthogonal vectors. What we really want is for them to be orthonormal. Okay, so if you go ahead and normalize each of these, I'm going to get -1 over the square root of 10, 3 over the square root of 10, and then 3 over the square root of 10, 1 over the square root of 10. If you want to go ahead and rationalize those, you can to put the square root on the top. That's up to you. So that gives me that my matrix P, where I've done A is equal to P, D, P transpose. P is going to equal negative 1 over the square root of 10, and 3 over the square root of 10, 3 over the square root of 10, and 1 over the square root of 10. And D is the diagonal matrix that's made up of the eigenvalues. So A is equal to PD, P inverse or P transpose, because we know that P is this orthogonal matrix. So that means that D is equal to P transpose AP. So by letting X equal P times Y, I know now that when I write my quadratic form in terms of Y, the matrix for my quadratic form is now D. So when writing the quadratic form in terms of Y, where X is equal to P times Y, or you can say Y is equal to P transpose X or P inverse X, okay? Then the matrix of the quadratic form is D. So if the matrix of the quadratic form is now this, by taking Q of Y is equal to Y transpose dy, if you multiply that out where Y is just Y1, Y2, I'm going to end up with just negative 7 Y1 squared plus 3 Y2 squared. Okay. So whenever you do this, okay, just make sure that you go ahead and orthogonally diagonalize that matrix. Then that diagonal matrix D is going to be the matrix of the quadratic form where you use Y instead of X, where we have done this change of variable. Just as a heads up, if they ever say to you, like, here's the quadratic form and they've done it in terms of X, they ask you to do the change of variable to Y, so you now have this quadratic form that has no cross product terms. And then if they say to you, what is the value of the quadratic form at X is equal to something, so they give you an X value, what you can do, instead of plugging the X values into the quadratic form in terms of X, you can do this change of variable and plug in X is equal to whatever they give you and multiply it by P transpose to get Y, and then you can plug the Y values into here with Y1 and Y2. So if you have the quadratic form both in terms of X and Y, where they have given you this change, or you may have to work it out for the change of variable from X to Y, so you've diagonalized that matrix, you know what the matrix P is. When you've done that, you can either plug in the X that they give you, so the X values, it could be like X is equal to 3, 5 or something, whatever they give you. You can then plug 3, 5 into here, multiply it by P transpose and get the vector Y, and then just plug in the Y vector into that new quadratic form. Or you can take that vector X is equal to 3, 5 and plug it into the original quadratic form. It is completely up to you. Okay. All of this that we have just learned is something called the principal axis theorem. So what this says is that for this n by n symmetric matrix A that you have, that is going to be this matrix of some quadratic form, you can always do an orthogonal change of variable. So when A is an n by n symmetric matrix, you can always do this orthogonal change of variable where X is equal to P times Y, where P is that orthogonal matrix, And by doing that orthogonal change of variable, it's going to transform the quadratic form x transpose ax into y transpose dy, where d is now diagonal instead of just symmetric, and it gets rid of those cross product terms. Okay, so we like this new quadratic form that has no cross product terms. It just makes stuff look slightly nicer. It makes calculations a lot easier, as we'll see later on. The reason that it's called the principal axis theorem is because the columns of P are referred to as the principal axes. So just be aware of that. And then y, because x is equal to P times y. Okay, y would be the coordinate vector of x with respect to the basis that is made up of the columns of P. So if you took the columns of P as a basis for Rn, then y would be the coordinate vector of x with respect to that particular basis. Okay, as we've always looked at before with coordinate vectors. Okay, y is just made up of the coordinates of x with respect to that basis that is made up of the columns of P. So what do the graphs of these quadratic forms actually look like? Well, if you look at page 406 in the textbook, they've drawn some of these graphs for you. It turns out that it all depends on what those eigenvectors or normalized eigenvectors are of that matrix A. Now, if A is diagonal, we know that the unit vectors are the eigenvectors of the matrix A. And so those form the axes, those principal axes for our particular quadratic form. So in this case, what it turns out is if A is diagonal, then we end up, depending on the values that are on that diagonal, you either get an ellipse, which is the graph of the quadratic form, or a hyperbola. So either one of these, depending on what the values on the diagonals are, you're going to end up with either an ellipse or a hyperbola, and they are based around those principal axes, those eigenvectors of that matrix A. When A is diagonal, that's just the unit vectors 1, 0, and 0, 1. Now, the issue comes when you have a matrix A for the quadratic form where it is not diagonal. So it's just symmetric, but it's not diagonal. And again, depending on the values in the matrix, you are going to end up with an ellipse or a hyperbola. But now they are going to be at an angle. And the principal axes, again, are going to be the eigenvectors of that matrix A. So they're going to be the columns of that matrix P, where A is equal to PD, P transpose. Now, those two eigenvectors, the two columns of P, are going to be the principal axes, which means that, again, your ellipse or your hyperbola are going to be centered on those axes. So they will always, the ellipse or the hyperbola will always be in standard position relative to either the standard basis 1, 0 and 0, 1, or with respect to the two eigenvectors for A, where we have transformed from the standard basis, this case using the columns of P, and now the columns of P form the basis, and so the ellipse and the hyperbola are going to be centered around those two new eigenvectors that form those columns of P. Okay, so again, if you have a diagonal matrix A, then your ellipse and your hyperbola are going to be in standard position relative to just the standard basis 1, 0 and 0, 1. But when A is not diagonal, we find that we have these other eigenvectors of A, and so our ellipse or the hyperbola is going to be in standard position with respect to those eigenvectors, which means that they are going to be at an angle compared to our standard axes. But compared to the principal axes, which are those columns of P, which are my principal axes, columns of P are the orthonormal basis for, in this case, R2. And we're going to have our ellipse and the hyperbola, in this case, are going to be in standard position relative to those instead of with respect to the standard axis. Okay, so keep that in mind when you look at those two pictures on 406. They've got the pictures for the ellipse and the hyperbola when you've got A being diagonal, and then the ellipse and the hyperbola where A is just symmetric, and they've given you certain examples there that you can look at. Now, we can actually classify our quadratic forms into 3 different types of quadratic form. There's actually 5 different types, but we focus on 3 of them. And that is a positive definite, a negative definite, and then an indefinite form of a quadratic form. So, if you find that your quadratic form, regardless of the vector x that is plugged in, as long as x doesn't equal 0, if you always find that your quadratic form is going to be positive, then you have a positive definite quadratic form. Now, if q of x, our quadratic form, is always less than 0 for any non-zero x, then we have a negative definite quadratic form. Okay. And finally, if you end up with this q, this quadratic form x transpose ax, such that for some values of x you're going to get something greater than 0, and for some values of x you're going to get less than 0, so q of x can be positive or negative, then that means that you have an indefinite quadratic form. Now, sometimes you may end up with a case, if we come up to these top 2 here, we'll look at the first one. Sometimes you'll end up with a case where your quadratic form may be greater than or equal to 0 for all non-zero x. So you may find that there are some non-zero x vectors that when you plug in x1, x2, x3, etc., when you plug those into your quadratic form, you're going to find that for some non-zero x's, so where all of your xi's aren't 0, you may find that your quadratic form might actually equal 0. In that case, it is called positive semi-definite. In the same way, if you have q of x is less than or equal to 0 for some non-zero x, so you find that there are some non-zero x's such that you still get that your quadratic form is equal to 0, but for all the others it's less than 0, then you have a negative semi-definite. So if you have q of x is greater than or equal to 0 for non-zero x's, then it's going to be positive semi-definite. And if q of x is less than or equal to 0 for all non-zero x's, you have a negative semi-definite. Okay. For example, if we let's take the quadratic form, q of x is going to equal 3x1 squared plus 6x2 squared. Okay. As long as I input non-zero x's, so as long as both x1 and x2 aren't 0, then I know that this thing is always going to be greater than 0, regardless of the x1 and x2 that I put in, whether they be positive or negative. This is always positive. So this thing here is positive definite. Okay. But let's say instead I just had, so x in this case is a two-dimensional vector with x1 and x2. But my quadratic form is just 3x1 squared, okay? In this case, if I took x1 equal to 0 and x2 equal to anything I liked, I've got a non-zero x in there, but I could still end up with a 0 here. But for any other x1 and x2, this thing is always going to be greater than 0. So this is positive semi-definite. So that's the difference between the two. Normally you'll find that one of the xi's is actually not in the quadratic form, even though you've got like a two-dimensional x here, only one of the xi's comes up. Now, how do we know when a quadratic form is positive definite, negative definite, etc.? Well, it turns out that the quadratic form, so Q of x is equal to x transpose AX. This is positive definite if and only if all the eigenvalues of A are positive. This is actually very easy to see because we've got this quadratic form. We know that we can rewrite this in terms of y and a diagonal matrix. Okay, so we could do that change of variable. There should be a y in there. So Q of y is equal to y transpose dy, where d is diagonal. If you were to expand this out, okay, remember D has the eigenvalues of A on its diagonal. So if you were to expand this all out and multiply it out, you would get lambda 1 y1 squared plus lambda 2 y2 squared, etc. Okay? So each coefficient of the yi's is an eigenvalue. So this thing here is going to be positive all the time as long as each one of the y's or x's doesn't equal 0. It's going to be positive as long as each of your coefficients, being the eigenvalues, is positive. Okay? So it's positive definite if and only if all the eigenvalues are positive. It's negative definite, as you would expect, if and only if all eigenvalues of A are negative. And in the same way, it's indefinite if you've got a mix of both positive and negative eigenvalues. Now, in the same way, we kind of expand this to then just look at this matrix A. If you have this positive definite quadratic form, the matrix of that quadratic form can then be said to be positive definite. So if you've got this quadratic form x transpose AX, and you find out that it's positive definite, then we actually say that the matrix A is positive definite. In the same way, if we find that this quadratic form is negative definite, then we can also say that the matrix of the quadratic form A is negative definite. So these terms actually apply to both the quadratic form and the matrix of the quadratic form. You can actually describe them in the same way. Okay. I will give you some homework problems that you guys can try on this chapter, and it's kind of doing a lot of rearranging of these quadratic forms and doing change of variables and that kind of stuff. So go ahead and try those. If you have any questions, let me know, and I will see you in the next video.